what we have been seeing is that CPU scheduling techniques. Okay, and before going to the detailed discussion about the rest of the topic, what we have been left out in the last class, let us will review what is happened in the last class. So, what is now we are going to be see the CPU scheduling. It is CPU scheduling, or may call it as process scheduling, or may call it as short-term scheduling. The CPU scheduling is the basis of multi-programming operating system. By switching the CPU among processes, the operating system can make the computer is more productive. The main objective of an operating system, that is, whatever it may be, to maximize the CPU utilization. So, already we have been seeing in the last class, whatever the processes which has been running on your computer system, this particular process is going to be defined as it is a continuous collection of CPU burst and IO burst cycles. Okay, the processes are classified into two categories. Number one is CPU bound process. Number two, IO bound process. A CPU bound process is having more number of CPU bursts than IO bursts, and IO burst is having more number of IO burst cycles than CPU burst cycles. And followed by what we have been seeing is that the scheduling algorithms has been classified into two categories. Number one, preemptive scheduling. Number two, non-preemptive scheduling. The scheduling algorithms are classified into two categories: preemptive and non-preemptive scheduling. Preemptive in the sense forcibly stopping the execution of one particular process and giving the control of the CPU to some another process. But whereas in the case of a non-preemptive, the CPU does not release its memory. CPU does not release its memory control until the process execution has been successfully completed. Okay, now coming to the last topic, this is that dispatch latency. The time it will going to be taken for stopping the execution of one particular process and giving response to another process is known as dispatch latency, which is already includes context, etc. Uh, Now coming to the next very important one is that scheduling criteria. So whatever the scheduling algorithms you are trying to design, these scheduling algorithms must satisfy the following 5 points. Number one, CPU utilization, throughput, turnaround time, waiting time, and response. Now you have to design an algorithm in such a way that the CPU utilization and throughput must be maximized, and turnaround time, waiting time, response time must be minimized. Okay, and we have been seeing okay, what are the different kinds of scheduling algorithms? Is that first come first serve scheduling, shortest job first scheduling, preemptive priority scheduling, round robin scheduling, multi-level queue scheduling, and then such kind of an algorithm is preemptive. If the arrival times are not specified, that implies all the jobs are, we are assuming that all are arrived at the same time, then it is called as non-preemptive. This is what we have been seeing in the last class. Now we'll move on to today's topic of discussion is priority scheduling. So, so what do you mean by priority scheduling? So the term itself it says that the term itself it says that the job which is having the high priority job is always executed first. The high priority job is always executed first. So it is this in this also we have both preemptive and non-preemptive scenarios. Why? Because okay, if all the jobs are arrived at the same time, then we're going to be schedule the jobs in a non-preemptive manner. In case if every moment, every clock pulse per time we consider the jobs, then in that case, it is a preemptive scheduling algorithm. Now, what is the main disadvantage? What is the main disadvantage of okay this particular priority scheduling algorithm? Um, Before going to the detailed discussion about disadvantage of preemptive scheduling algorithms and priority scheduling algorithm. Okay, first of all, a preemptive priority scheduling algorithm will preempt the CPU if the priority of a newly arrived process is higher than the priority of the current running process. But whereas in the case of a non-preemptive priority scheduling algorithm, it will simply put the new process at the end of the ready queue. Of, what is the main disadvantage of this algorithm? The main disadvantage of this algorithm is that okay, it is going to be suffers with starvation problem. What do you mean by starvation? Low priority process sometimes it never gets the Sir, some disturbance is coming. So, in order to overcome, hello, everyone is there on the line? Is it okay? The solution for this to the problem is indefinite blockage. Okay, the solution for this. Okay, so the solution of the problem of indefinite blockage of a low priority process is known as aging. The solution to the problem of indefinite blockage of a low priority process is aging. What is aging? Aging is a concept continuously adding priority to the waiting process. Aging is a process of continuously adding priority to the waiting process. The low priority process is going to be waiting the most of the time in the ready queue. After wait, what is aging concept will do is that after waiting some amount of time, okay, the priority of the process is going to be increased. Again, after waiting some amount of time, again the priority is going to be increased. So that what happens is that what happens is that after some amount of time, definitely this process is going to be the most high priority process. Now we're going to see the problem by means of a problem. Okay, the highest priority job is always executed first. In this, we are going to see only one case that is called as a non-preemptive case. There are 5 processes are running in my computer system. Okay, P1, P2, P3, P4, P5, and the bus times has been specified, and the priorities also specified in this column. The first column is representing for the set of processes, and this is the burst times, that is how much amount of time that is required to complete your process, and this is going to be called as the priority of each and every process. Now we'll see, and they ask you to calculate what is the total average waiting time. Okay, this is a problem what we got and get. Okay, a 1 mark question. So now in order to execute process P1, it requires only 10 milliseconds. It requires 10 milliseconds. The priority of this process is 3, and in order to execute process P2, it requires only 1 millisecond. Okay, the priority of this particular process 1. In order to execute process P3, okay, the priority it requires 2 milliseconds, and the priority is 4, and so on up to like this. Now the Gantt chart representation of the scheduling of these jobs is, now we observe it, the P2 is having high priority, and the next one, okay, P5 is the next high priority process, and P1 is the next high priority process, and P3, so on like this. Okay, now correspondingly among all these particular 5 jobs, who is having high priority in the sense, the process P2 is a high priority, so that first of all we'll give you the CPU control to P2. So it executes how much amount of time? It is for 1 minute, 1 millisecond, that is P2 is completed first second. And after that, the process, the second high priority is P5. It requires 5 milliseconds. 1 plus 5, that it is completed at 6th. Okay, so it is completed at 6 second. And again, next high priority is this one, P1. It requires 10 milliseconds. So that is 6 plus 10, it becomes 16. And after that, okay, and next high priority is 4. That is P3, it requires 2 milliseconds. So 16 plus 2, it is equal to 18. And after that, 18, the last one is going to be 4. It requires only 1 millisecond. 18 plus 1, now it becomes 19. So now, coming to the next one, the waiting times of each and every process now we are going to be calculated. The waiting times of this process, the waiting time of process P1 is 6 seconds. Why? Because it has to be wait until process P2 and process P5 has to be completed. The waiting time for process P2 is 0. Okay, it is not waited for anyone. Immediately, once it is entered into the queue, immediately it has been scheduled. The waiting time for process P3 is 60. The waiting time for process P4 is 18. The waiting time for process P5 is 1. Now we calculate the average waiting time is equal to 6 plus 0 plus 16 plus 18 plus 1 by 5, that is 8.2 microseconds or milliseconds, what it means. That's it. This is a non-preemptive case, and similarly we will also have a preemptive case also. In this we have another column is called it as arrival time. So we need to see that at every arrival of new process, we need to see that who is having high priority. So once, okay, the currently arrived one is a high priority, by forcibly stopping the execution of the currently executed one and giving the control of the CPU to the high priority process. In a similar manner, how we have been done in the last class, that is, okay, non-preemptive case of preemptive case of this particular one. In this, you are having specified arrival times. So P1 is preempted and control is given to P2. Why? Because it is shortest time. In a similar manner, okay, we need to give control of the CPU to another process in case that process is having high priority than the currently one. That's it. Now we move on to the next kind of scheduling algorithm is round robin scheduling. Next kind of scheduling algorithm is round robin scheduling algorithm. So what is this round robin scheduling algorithm? So it is purely based on time sharing operating system. It is purely based on time sharing system. You know what is time sharing operating systems? So time sharing operating systems, in the sense, a small amount of CPU time is going to be dedicated for each and every process. Okay, how much amount of time it has been dedicated is called it as time quantum. Within the time quantum, the process may be completed or may not be completed. In case if it is not completed, it has to wait until the next time slot is comes up. This is going to be called it as time sharing operating system. Now, round robin scheduling is going to be purely based on time quantum. That is time sharing operating system, round robin scheduling. Each process gets a small amount of time for execution with the CPU. That amount of time is called as quantum, usually 10 to 100 milliseconds. After this time has elapsed, the process is forcibly preempted. After this, operating the process is preempted and added to the end of the ready queue. Okay, why? Because CPU is going to be dedicated a small amount of time on each and every process within the time the CPU. The process may be completed, may not be completed. That implies your timer control is continuously giving an interrupt to the CPU after completion of every quantum, so that corresponding immediately CPU does simply stop the currently whatever it executing and shift it to the next job in the queue. So that's why this round robin scheduling is preemptive scheduling algorithm. This is preemptive scheduling algorithm. Now, how do you? So now, coming to the performance considerations of this round robin scheduling algorithm. Okay, if time quantum is large, it's simply acting like a first in first out scheduling algorithm. If the time quantum is high, if the time quantum is high, that is Q is large in the sense I have been specified as time quantum. If the time quantum value is taken as a large, it is works like in a first in first out. So which job is arrived in the first, that job is going to be always executed first. If Q is small, what happens? If time quantum is very small, CPU is going to be frequently switching from one particular job to another job. So what happens is that before switching from one particular process to another process, before switching from one particular process to another process, first of all, it need to save the status of the current process where it has been stopped somewhere in the stack, and and again restore it at a later stage. That implies the maximum amount of time of CPU is simply wasting for saving and restoring. This particular concept is known as context switch. Already we have been seeing in the last class. This kind of a concept is known as context switch. This kind of a concept is known as context switch. Okay, so if the queue is small, your round robin algorithm is going to be suffering from most of the time is wasting for doing context switch overheads. Now we'll explain this particular round robin scheduling algorithm with a small problem by taking a small problem as an example. Now we'll see. There are three processes are running in my computer system. There are three processes are running in my computer system. Then process and bus times is also specified. In order to execute process P1, it requires 24 milliseconds. In order to execute process P2, it requires 3 milliseconds. In order to execute process P3, it requires 3 milliseconds. Now the time quantum has been specified as 4. Time quantum is specified as 4. Now what happens? Now we'll see. The time quantum has been specified as 4. Let us take the Gantt chart representation. First of all, CPU dedicates a 4 milliseconds on process P1, 4 milliseconds on process P2, 4 milliseconds. I already told that during this time quantum period time, the job may be completed, may not be. This is for the time quantum period time. This job may be completed or may not be completed. But the time quantum is 4, but it requires only 3 milliseconds so that the P2 is completed. Again, the next time quantum is allotted for Process P3, it is also completed at 10. So 4 plus 3 is 7, 7 plus 3, then there is no other processor there. So what happens is that again CPU will going to be alerts for okay, 4 milliseconds for P1. Again, next no jobs are arrived, so that P1, 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 4, 4. For 10 plus 4, 14, 14 plus 4, 18, and so on like this one. Now we need to calculate the waiting times of the waiting time of each and every process. Now we'll calculate. How do you calculate it? Waiting time of P1 is equal to 0. The waiting time of P1, 10. Earlier it has been stopped at 4. That is 10 minus 4. It is 6. And next one, 14. This one. But earlier stopped at 14 and started at 14. That implies it's 0. Earlier stopped at 18. Again it started at 18. There is no waiting time. 0. Similarly, 0, 22 minus 22, 26 minus 26, that is 0. So the total waiting time of process P1 is equal to 6. Now coming to the next one. The waiting time for P2 is 4. The waiting time for P3 is 7. That is, now the total average waiting time is equal to 6 plus 4 plus 7 by 3. That is 5.67 milliseconds. That is 5.67 milliseconds. That's it. So here you can observe it. P1 is preempted and the control of the CPU is given to P2. That's why, so within the time quantum, the job may be completed or may not be completed. Your CPU execution is forcibly stopped and control of the CPU is given to someone person. Hence, the round-robin scheduling algorithm is purely preemptive scheduling algorithm. Round-robin scheduling algorithm is purely preemptive. Now, coming to the glance, or may call it as final review, before going to the next topic of discussion. Okay, so we have been seeing 4 scheduling algorithms. First come, first served is purely non-preemptive. Shortest job may be preemptive, may not be preemptive. Number 3, priority scheduling, preemptive or non-preemptive. And round robin is purely preemptive. Already we got one question in GATE. They have been given this particular 4 algorithms and asked you to specify which one is preemptive and which one is non-preemptive. So according to that, you need to answer that question. Now, we will move on to the next very important one is that multi-level queue scheduling. Okay, that is another class of scheduling algorithms has been created for the situation in which processes are easily classified into different groups. So already from the previous class discussion, you already know that there are different types of queues are there in your computer system. You know that what is that particular queues? Number 1, ready queue, which is contains. Number 1 is ready queue, which contains the set of all jobs. There's a set of all jobs which are waiting for the CPU to continue the execution. Number 2, IO queue. So each and every IO device will maintain one queue that is called as IO. And job queue. There are several kinds of queues are there. So the scheduling, either your CPU is completely responsible for scheduling the jobs on each and every queue. There are how many queues are there? There is ready queue is there. Job queue is there. IO device queues are there. So your scheduling algorithms is always responsible for selecting some of the jobs and try to do some action. Suppose your job from ready queue to CPU to make the CPU execution like this. Now the scheduling decisions are not going to be done in one particular level. So first of all, the CPU has to be decided that which queue I need to shift. First of all, the CPU has to be decided that which queue I need to shift. And in that, again, in that particular queue, which job I need to execute. There are 3 queues are there. Q1 ready queue, Q2 job queue, and IO queue. There are 3 queues are there. First of all, the CPU has to be decided that whether I need to go for which queue. And after entering that particular queue, again, in that queue, which job is going to be executed first? That is, the scheduling decisions are not going to be happen in one particular level. The scheduling decisions are going to be happening more than one level. So that kind of a scheduling algorithm is going to be called as multi-level queue scheduling algorithm. That implies where the scheduling decisions are not going to be happening in one particular level, the scheduling decisions are going to be happening more than one level. So in order to better understanding of a student, now I'll We're going to be dividing this particular problem into like this. If the ready, let us consider only ready queue. The ready queue has been internally partitioned into two separate queues. According to Unix operating system, according to Unix operating system, the ready queue has been partitioned into two different queues. What is that particular queues? Number one, foreground. Number two, background queue. What is foreground? What is foreground? This is also going to be called it as interactive jobs. Number two, background in the sense batch jobs. What is foreground? So what is foreground means that a process is said to be in foreground. That implies while executing such kind of a process, it needs an interaction with the user. While executing such kind of a process, it needs an interaction with users. Such kind of jobs are going to be called as foreground jobs. Whereas in the case of background, while executing such kind of a job, there is no need of making interaction with the user. Let us take an example. Suppose if you are taking a printout on a piece of a paper. Suppose if you're taking a printout on a piece of a paper. So while printing the particular content, okay, user may not be need an interaction with the printer. That's simple. You can issue a command and you can do the normal execution. That's enough. Such kind of jobs are going to be called as background. Suppose if you are copying one file to another file, while copying that information, there is no need of making any interaction at all. That is background. So while executing such kind of a process, whatever the processes which are running in your computer system, these processes are classified into two categories. Number one, foreground. Number two, background. Foreground in the sense while executing such kind of a process, it is always needs an interaction with the user. But whereas in the case of a background, while executing such kind of a process, it does not. Suppose if he chooses foreground, in the foreground there is multiple jobs are there. In the jobs, which job I need to execute? Now the scheduling decision is going to happen in two levels. Hence it is going to be called it as multi-level queue scheduling. Now let us take another example. Suppose let us take an example. Okay, an algorithm with 5 queues. Now I'm assuming that there are 5 queues in my computer system. Okay, how I have been classified generally. Okay, system processes, interactive processes, interactive editing processes, batch processes, and student process. There are 5 queues are there. System processes in the sense assemblers, learn the programs which is required to run your computer system. the programs which is the set of software programs which is going to be required to run your computer system is going to be called as system processes. That is assemblers, loaders, linkers, compilers, etc. These all comes under the category of system process. Interactive process. While executing such kind of programs or processes, it is always needs an interaction with the user. That is interactive processes. Interactive editing process. While executing such kind of this one interactive, while it is always every moment of time it is going to interact with the user. Let us take you're typing a document in MS Word. So while typing, you're going to be seeing on each and every word what you are going to be entering. That kind of jobs are going to be called as interactive editing. Batch process, a group of jobs are going to be submitted at the same time and executing it. We'll see output at a later stage. And the program which is going to be run by the student is known as student processes. Suppose let us take an example. Now this is a 5 queues. Okay, so among this particular 5 queues, okay, how the CPU will going to execute the jobs? First of all, in level 1, the CPU has to be decided that whether I need to go for system process queue or interactive process queue or interactive editing process queue or batch process queue or student process. This is level 1. And level 2, suppose if he has been selected interactive process. If this interactive queue is also having set of jobs. Among these particular jobs, which job I need to execute first? That is level 2 decision. So level 1, first of all, it has to decide that, okay, which queue I need to go. And second level, in that queue, okay, which job I need to execute. That's it. This is going to be called the second exam. Now I have been concluding that the scheduling decision is not going to be happen in one particular level. The scheduling decision has to be happen in 2 levels. Okay, so in case it may be more than 1 level, hence it is called as multi-level queue scheduling. Now, how do you schedule this particular job? Suppose, let us take an example. Okay, for this second example, I have been given priorities. The system process queue is the first priority, and this is second, and interactive editing process third priority, batch process fourth priority, and student process fifth priority. I have been given the priorities of the jobs like this. Then how it is going to be executed? Okay, the CPU is always executing system processes queue. Once system process queue is empty, then CPU is switched to interactive processes. Once this is empty, and then it goes to interactive like this. Then what happens is that, suppose you have completed all the jobs in system process, and again you come back to interactive processes. While executing one job in interactive process, another new job is going to be arrived into the system process queue. What happens? According to the priority scheduling, okay, the highest priority job is always executed first. Simply you are stopping interactive process and you are shifting to system process. Again, after completion of this, again you come back to interactive process. After completion this, again you are venting into interactive editing process. While executing this process, in case if any jobs are entered into this particular two queues, CPUs immediately stop the control of an interactive editing process and again subsequent to these two queues. Then what happens about student processes? He is completely waiting. Okay, in case if you want to execute student process, all the above four queues must be empty. Otherwise, the student process are not allowed to continue. That implies there is a long time delays occurred for executing student processes. So that's why they have been defined that priority scheduling is not suitable. Then they have been come to another kind of a technique, round robin scheduling. Another possibility is to time slice between the queues. Each queue gets a certain portion of the CPU time which can the schedule among various processes in its queue. Let us say CPU will going to spend a small amount of time in system process queue, and after that interactive process, after that interactive editing process, after that batch processes, after that this one. A small amount of CPU time is going to be dedicated for each and every queue, so that all the jobs are going to be scheduled like this. Let us take an example. Okay, suppose if in case you take this particular case foreground background, 80% of the time you are taking for executing foreground and 20% of the time for executing this one. Okay, the foreground queue can be given 80% of the CPU time for round robin scheduling among its processes, whereas in background queue it receives only 20% of the time to give its process to in first come first serve manner, like this. This is going to be called it as use first come first served or priority scheduling, whatever it may be. Now we observe it, CPU is frequently switching from one particular queue to another queue. Yes. Now the main disadvantage of this multi-level queue scheduling algorithm is that the CPU is switching between the queues. The most of the time CPU is switching between the queues. So in order to work on this particular problem, again they comes with a new technique is going to be called as multi-level feedback queue scheduling. Again, the happen comes with a new technique is going to be multi-level feedback queue scheduling. A process can move between various queues. Aging can be implemented in this way. So, being how we will see this one. Before going to the detailed discussion about how to implement multi-level feedback queue scheduling algorithm, so the minimum parameters which is going to be required to implement this algorithm. So, how do you? So the minimum number of parameters is that these are the different queues. This is Q1 and this is Q2 and this is Q3. There are 3 queues are running in my computer system. Okay, the CPU is not going to be moving between all the queues. CPU is going to be fixed at only one queue. Now I'm going to be fixing at the CPU in the first queue at quantum is equal to 8 in the first queue. Now, so there are 3 queues are maintaining. This queue, all queues are linked together. Now what happens is that according to them, each and every queue is having some priority. Whenever a new job is arrived into the computer system, then according to its priority, it may be placed in first queue or second queue or a third queue. So after placing that, what happens is CPU will not going to be moving from one particular queue to another queue. The CPU is always stick down. The CPU is always stick down in the first queue itself. CPU is not moving anywhere. So what happens is that if the job is placed on first come first served queue, after some amount of time, the job priority is automatically increased and the job is jumped from this queue to this queue. And after that, after some amount of time, again these particular jobs are going to be shifted from this particular place to this place, or you can do like this. That's it. This is what I mean. This kind of a concept is known as, you already know that, aging. What is aging? Continuously adding priority for the waiting process is known as Aging, continuously adding priority for the waiting process is known as this one. A process can move between the various queues. Okay, depending on the priority, aging can be implemented. Now, in order to implement this particular one, that is, no job is suffering from starvation. Why? Because after waiting a some amount of time, the job may be promoted for high priority, or it may be something. It may be after some amount of it may be promoted to high priority like this. Okay, no job is suffered from deadlock or starvation. Now, so in order to practically implement this particular algorithm, so what are the different parameters you need to consider? Number one, the first very important thing is that number of queues. The first very important one is how many number of queues you want to maintain. First of all, you need to decide that, okay, how do you maintain, what are the different number of queues? Number two, what is the scheduling algorithm of each and every queue? In this, I have used round robin scheduling. In this, I have used round robin scheduling with time quantum 6C. In this, I have used first come first served scheduling. So a second very important one is that you need to decide what is the scheduling algorithm of each and every queue. And coming to the third one, so method, okay, when to promote a process or when to demote a process. If a process is going to be waiting for a long immediate of time, according to the aging concept, you need to add a priority and you need to shift from one particular queue to another queue. That implies you need to write a method which can be used to determine when to upgrade a process. Similarly, and you need to write another program. Suppose one process continue utilizing the CPU time. So after some amount of time, you need to demote that process. It is continuously running. You need to give priority for other process also. Then you need to write another method which can be used to determine when to demote a process. That is, and finally, the fifth very important one is the method used to determine which queue a process will enter into. Process needs a service. So once a new job is arrived, you need to decide whether it is going to be entered into a first queue or whether you need to enter into second queue or it may be in this one. So you need to adapt some method. You need to write one program which will going to be decide that. So this job is going to be placed on which queue. This job is going to be placed on which queue. Now, so far what algorithms we have been seeing, this all are going to be concerned about a uniprocessor. Now we'll move on to the next very important topic is multi-processor scheduling algorithms. Next we are going to be move on to multi-processor scheduling algorithms. So what is this multi-processor scheduling? So from the earlier so far so many times I have been discussed that in multi-processor scheduling there are more than one CPU is available for executing processes. More than one CPU can be simultaneously reside on a same machine. They are closer to communicate. In order to establish the communication between the processors, if they're using same clock pulses, same buses, same memory, then such kind of a thing is going to be called as parallel system technology. In order to establish the communication between the processors, okay, parallel system technology, or may call it as then okay, in order to establish the communication between the processors, if they're using separate clock pulses, separate buses, and separate memory, hence it is going to be called as distributed system technology. So whenever your computer system is equipped with multiple CPUs for executing processes, now how can you decide the scheduling? How can you decide the scheduling? Now, before going to the detailed discussion about the scheduling techniques, now we're going to see that this process organization. Why? Because this is very important. Why? Because scheduling can be done before writing scheduling algorithm. These precautions has to be made. The processor organization, multi-processor organization is classified into two categories. Number one, symmetric multiprocessor organization. Number two, asymmetric multiprocessor organization. Symmetric in the sense, homogeneous process organization, we may call it as symmetric one. All the processor of same kind of configuration. Asymmetric multiprocessor organization. Then it is going to be called it as asymmetric multiprocessor organization. Then it is also called it as heterogeneous processor organization. Now, why we are talking about these two things? Suppose let us take in homogeneous organization. If a process is compiled on one processor, if a process is compiled on one particular processor, that is CPU, if a process is compiled on one particular CPU, then it should be executed on any other processor. Why? Because all are same. All are same, there is no problem. Whereas in the case of heterogeneous process organization, if any process is compiled on one particular CPU, it should be executed on the same processor. It cannot be executed on some another processor. It cannot be executed on any other processor. Why? Why? Because let us take I3 and I7. The addressing modes and instruction formats of I3 is completely different from addressing modes and instruction formats of I7. So we cannot give a guarantee that a program which is running on one processor may not be run in some another processor. That's why in heterogeneous organization, in case if any process is compiled on one particular CPU, you need to schedule the job in a same processor for executing. You should not take another processor. That is a very important thing. Okay, now everyone knows that why Java is very popular today. The Java is very popular today because of only two reasons. Number one is platform independent. Number two is architectural neutral. Platform independent in a sense, everyone knows that Java programs are not depending on any native of the operating system. So that is a separate topic. We'll see at a later stage. Suppose in case a program running on Windows okay, can you give guarantee? Suppose let us take an example. You have been done a project for Windows NT operating system. Are you give a guarantee that the same program will run on Unix? No, it cannot be run. A program which is running on Windows NT may not be run in Windows Unix. Because of an operating system differences, it cannot be run. Why? What is the differences? Let us take already you know that what is a process. A process can be thought of as it is a program in execution. In order to execute a particular process, you may require resources like CPU cycles, memory cycles, and IO devices, etc. These all resources are under the control of an operating system. So before executing any particular process, first of all, you have to make a requisition to the operating system. I want these resources. If the resource is available from operating system, then it simply gives you and it allows to execute. And once your completion is your process execution is complete, again you need to return back all these particular resources to operating system. That implies your process may need a lot of communication with operating system. How this communication will occur? By using a system call. The Windows NT system calls is different from Unix. So once a system calls difference is occurred, a process which is running on one operating system may not be run in some another operating system. That is the first very important one. Okay, now coming to the second one, architectural neutral. What is architectural? What is architecture? Architecture in the sense, the addressing modes and instruction formats of the CPU. Okay, we cannot have a same kind of addressing mode instruction formats in all the process. That's why a program running on one processor may not be run in some another processor. Why? Because addressing modes and instruction formats of the CPU is different. So due to that particular one, so in homogeneous there is. Now what happens is that CPU1 is for Q1, CPU2 for Q2, CPU3 is for Q3, CPU4 is for Q4. Now, so each and every queue is having separate scheduling algorithm according to CPU. Like this, you are going to be design a scheduling. So depending on what happens is that whenever a job is going to be entered into your computer system, that you need to decide that the job is going to be entered into which queue, so that there's one. Like this, you are going to be implementing it. You are maintaining a separate queue for each and every processor. What happens is that some queues are completely busy, some queues are completely empty. Some queues are completely busy and some queues are completely empty. So more number of processors. That is for first one. Okay, and separate each and every processor maintains a separate queue. That implies in this approach, each processor is self-scheduling. Each processor examines the common self-scheduling algorithm, and each processor is going to be selecting one process from the queue and execute it. The disadvantage of this one is CPU may be completely busy or CPU may be okay. Now they are going to be maintaining a common ready queue. We are having only one queue. Whenever the CPU becomes idle, it has to come to this particular queue and select a job and execute it. But so in this, it is very good solution. But you need to take a precaution that a job cannot be scheduled or executed by more than one CPU at the fastly completed its jobs, then that processor becomes as a master and rest of all the slaves. So we conclude that there is no one is completely a master, no one is completely a slave. So no one is completely a master, no one is completely slave. So everyone is master, everyone is a slave. This kind of a scheduling algorithm is going to be called as multi-processor scheduling algorithm. And coming to the last concept of discussion in this is that real-time scheduling. The last concept of discussion is real-time scheduling. Already we have been seeing that real-time operating system. What is this particular real-time system? Real-time operating system. The critical tasks must be completed on a given guaranteed amount of time, otherwise the system is going to be failed. That is, in case if any operating systems has been designed with the principles of time constraints, then such kind of an operating systems are going to be called as real-time operating system. In case if any very important one is soft real-time system, and soft real-time system, each and every job while submitting to the operating system, it specifies two things. Each and every job while submitting to the operating system, it specifies two things. That is, how much amount of time that is required to complete the job and what is its deadline. The CPU will going to be schedule the jobs in such a way that no job is going to be scheduled after its set deadline. But this kind of scheduling is not guaranteed as to when critical real-time process will going to be scheduled. Why? Because if two processes are going to be required at the same time response with the same deadline, so we cannot process it. So there is some possibilities are there, and we'll see. Now, now, coming to the first one, how do you implement this particular this one? Let us take before going to the detailed discussion about the practical implementation of real-time scheduling. So first of all, you must know some of the important things while designing a real-time operating system scheduling algorithms. Why? Because this, without knowing this particular thing, you cannot write a scheduling algorithm for that. What is this? So coming to the first one, already I spoke in the last 4 sessions. Okay, what is an interrupt? An interrupt is nothing but signal or received by the microprocessor indicating that one external IO unit want to communicate with CPU. What is an interrupt? An interrupt is a signal which is received by the microprocessor indicating that one external IO device want to communicate with CPU. What is an interrupt? An interrupt is a signal which is received by the microprocessor indicating that one external IO device want to communicate with CPU. Now, already happens in told that while executing a low priority process, a high priority interrupt is encountered. What you need to do? The low priority process is preempted and the response is given to high priority process. But before preempting a low priority process, first of all, you need to save the status of the current low priority process where it has been stopped. You need to load the new process and set the starting address of the program to program counter for initiation of execution. Okay, these all things has to be done. Okay, you need to save the current status, load a new process and set the starting address and start. This is what is happening. Now, while executing a high priority process, when a low priority interrupt is encountered, we are not doing it all. Simply add the job in ready queue at the end of the queue and do the normal execution. That is not at all a problem. That is the first very important thing. You please try to remember that while executing a low priority process, whenever a high priority interrupt is encountered, then the low priority process is preempted and the response is given to high priority process. That is the first very important thing. That is, see, while executing, one task is running in my computer system. I got an interrupt. Whenever an interrupt is encountered, immediately the control is transferred to interrupt vector table. Then interrupt vector table simply determines interrupt vector table. That, okay. So first of all, you need to decide whether it is a maskable interrupt or non-maskable interrupt. That is, if the maskable interrupt, I can simply ignore it. There is no problem at all. In case if it is a non-maskable interrupt, I need to immediately respond it. But before responding that, I need to decide that which is having high priority. Then, after determining high priority, suppose the currently received one is a high priority. Immediately, what I need to do is that whatever the task T I am running, I need to save this particular status and load the new process. That is going to be saving and restoring the status of that is going to be done by a program known as context switch. It is done by a program known as context switch. Then interrupt service routines are responsible for loading that high priority process and set the starting address of the program and start the high priority process. So if the job is, suppose let us take, while running a task, you got an interrupt, okay, and they asked you to service the interrupt within 10 milliseconds. But the time taken for determining the interrupt time, the time taken for context switch, the time taken for running IOSR is more than 10 milliseconds. I cannot able to do it. This is acceptable only if the response time is in acceptable limits. Otherwise, I cannot do it. So the minimum time that is required to switching from one task to another task is for doing these three activities. Let us take this. In order to do this particular three activities, I will take 10 milliseconds. But if any high priority interrupt is requesting a service within 5 seconds, I cannot able to provide it. So that I cannot design a real-time operating system. So in case if you want to design any particular real-time operating system, whatever the time limit which is required, it should be in acceptable limits. Otherwise, it is not possible. And that's it. This is only a one level of consideration. This is only one level of consideration. We'll see how the bit is comes in exam gate examination. We'll see 1 minute after this completion of this topic. Now, not only for this time, we also have data conflicts. We also have data conflict. Okay. So, of course, this is the basis for the next topic of discussion, that is process synchronization. Suppose in case if any data item is shared by more than one processes at the same time, in case if any data item is going to be shared by more than one process at the same time, if you are not using any proper security mechanism, the data will going to enter in the inconsistent state. In order to overcome this inconsistent state, we are using the concept of synchronization. The one of the best synchronization technique is locking. That implies before executing any particular process, first of all, you have to make a lock on the data item. Once the process execution is successfully completed, again you need to remove the lock. In case if you are not using locking mechanism, the data is in complete state, the answer is always wrong. That implies while executing a low priority process, when a high priority interrupt, please observe this diagram. Okay, high priority interrupt is encountered. This is interrupt processing. That implies you need to determine what kind of interrupt is, what is its priority. In case even though if it is high priority, I cannot be able to immediately switch it. I need to see that in case if any data is going to be shared between these two processes. In case if any data is shared between these two processes, I need to release the locks. That implies the conflict is the conflicts has to be resolved. The conflicts has to be resolved. After resolving the conflicts, that is after resolving the locking, after resolving the locking, what you need to do is that then you need to give for dispatcher. You know what is a dispatcher? So dispatcher is responsible for doing context switch, saving and restoring, that is, and followed by loading a new program, setting starting address, everything is going to be done. After that, then real-time process will going to be executed. So that is the minimum time that is required to respond. A real-time process is that. Okay, suppose let us take an example. Suppose for interrupt processing, 10 milliseconds, this is 10 milliseconds, this is 10 milliseconds, totally 30. Suppose in case if any real-time process comes and asks you to respond within 25 milliseconds, it is not possible. Why? Because this is the minimum time that is required to respond a real-time process. Suppose in case if you want to design in case if you want to design any real-time operating system within this particular time limits, this is not possible. So you need to design an operating system like this. This total amount of time for resolving the conflicts and dispatching is going to be called as dispatch latency. So 1 year we got a question like this. Okay, what is this question? What is the minimum amount of time for responding an interrupt? Number 1, A, okay, first of all, determining the interrupt type. Number B, determine the interrupt type is context switch. Number three, question number, option three, determine the interrupt type, context switch plus ISR. D, so determine the interrupt type, context switch, interrupt service routine, and data conflicts. So what is answer? Answer is D. So that implies whenever a real-time process has to be respond, the minimum time required to complete to respond, that one is number one, determine the time required to determine the interrupt type, the time determine use it to switch from one particular process to another process, the time you required to load the new process and setting the starting address, the time required to resolve the conflicts. That's it. This is completes our discussion about process scheduling. This is completes our discussion about process scheduling. Now we move on to the next topic of discussion. So now we'll go into the next topic of discussion in process management is process synchronization. This is really says that the heart of operating system, and we can also, this is really what generally computer science people are going to be really doing a challenging tasks in software industry, that is data sharing problems, which is going to be dealt in process synchronization. Now we'll go into the process synchronization. So what do you mean by this? So what do you mean by processing? So before going to the detailed discussion about process synchronization, already we have been seeing that multi-process organization. Multiple processes are residing in your computer system. There are multiple processors are residing in a computer system. They are all executing. Their execution is going to be classified into two categories. Number one is going to be called it as independent process organization. Number two is going to be called it as cooperative process organization. This is already done in the last class. Okay, the multiple process two is cooperative process organization. Coming to the first one, independent. Whenever two processes are set to be dependent, providing while one is executing, if does not affected by any other processes. That implies clearly I'm sharing that there is no common resources are shared between the processes. There is no common resources are shared between resources. There is no common resources are shared between the processes. That is going to be called as independent process organization. Now the second one is cooperative process organization. Whenever two processes are execution is said to be cooperative, provided one is executing, it can affect or affected by other processes. Can affect or affected by other processes. That implies both are sharing some common resources. So that are going to be called as cooperative process organization. That is, you are also going to be called it as concurrent process execution, or you may call it as cooperative process organization. That implies the processes may be can be executed concurrently and may be interrupted at any time by terminating or by partially completing its execution. What is the meaning of this? Already I told that according to multi-programming, more than one process is simultaneously reside in main memory. During the execution of one particular process, in case if any process is required an IO operation, the CPU is switching from one particular job to another job. This is one of the case. In case of a time sharing operating system, in case if it is a time sharing operating system, in case if it is a time sharing operating system, in case if the time quantum is completed, again the CPU has to be switched from one particular process to another one. That implies your CPU control is partially CPU control is switching from one particular process to another process before completing the execution. Suppose while executing a low priority process, whenever a high priority interrupt is encountered, the low priority process is preempted and the response is given to high priority. That's enough. This is the different cases where your CPU is going to be switching from one particular process to another process. But now the problem is, in case if these processes are sharing any particular data, if this particular process are sharing any particular common data, in case if any one process is in the midst of update, due to some problems, it may be a multi-programming or it may be a time sharing or it may be a high priority interrupt is encountered, CPU switches from one particular job to another job. What happens is that the data is going to be entered into inconsistent state. The data is going to be entered into inconsistent state. The data is going to be entered into inconsistent. In order to overcome this inconsistent state, in order to maintain the data consistency, we require some mechanisms to ensure the orderly execution of events. That is going to be called it as cooperative, the ordering, that is called it as process synchronization. That is called it as process synchronization. What is process? A process synchronization is a set of tools. A process synchronization is a set of tools which will try to see that the data will not going to be enters into inconsistency. A process synchronization is a set of tools or mechanisms to see that there is an orderly executive manner of cooperating processes. That's it. How can you understand this problem? Let us will see what is cooperative process organization. Already we have been seen in the fourth session, bounded buffer problem we have been seen. So what is bounded buffer in the sense? There is a practical limit on the buffer size. There is a practical limit on the buffer size. There is a practical limit on buffer size. So producer and consumer both are going to be uses this particular buffer for this one. Let us take an example. Already last class we have been seen producer consumer problem. So producer is producing items into the buffer, consumer consuming from the item from the buffer. The data structure which is required to implement this particular bounded buffer problem is the circular queue. Okay, you already know that in a circular queue, in order to distinguish when the queue is full, when the queue is empty, we need to use an additional variable called as counter. A counter is used to keep track of how many number of elements that is presented on the queue. Okay, counter is used to specify how many number of elements that is presented in the queue. Let us take an example. If my buffer size is 50, so that implies if counter is equal to 0, that is buffer is empty. If counter is equal to 50, then my buffer is full. Okay, now what happens is that suppose initially, let us take an example, my counter value is 5. That implies the number of items in the buffer is 5. If the producer is producing one item into the buffer, the counter value is incremented by 1. Now it becomes 6. Now, after that, the consumer is consuming one item from the buffer. Then after that, what happens is the counter value is going to be decremented. Counter value is decremented. Counter value is decremented. Now, so now both the producer and consumer are using one variable, call it as counter. Whenever producer producing an item into the buffer, the counter value is incremented. Whenever the consumer consuming an item from the buffer, the count value is decremented. Now, producer process, consumer process, both are cooperating processes. Both are sharing a common variable, call it as counter. Producer is always incrementing, consumer is always decrementing. This is what it means. Now, if you are not using any proper security mechanism for this counter value, now the data will going to be enters into inconsistent state. The data will going to be enters into inconsistent. The data will going to be enters into inconsistent state. The data will going to be enters into inconsistent state. The data will going to be enters into inconsistent state. Now, let us we'll see with an example. Already this algorithm we have been seen in the last class. That is, whenever a producer want to produce an item, okay, first of all he has to see that what is the counter value. if the counter value is equal to buffer size, that means I have been put in a semicolon for this loop. That implies this loop is not valid for any statement. By default, any control structure is valid for only one statement. If you put a semicolon for any loop in C language, it is not valid for any statement itself. It is going to be struck. That is, while if counter is equal to buffer size, that indicates buffer is already full. You are not allowed to produce any item onto the buffer. Why? Because buffer is already full. Suppose in case if counter is not equal to buffer size, then what happens? You can allow to produce the item into in variable. So in is a pointer pointing to placing an item. Out is a pointer pointing to removing an item from the buffer. So in is equal to in plus 1 buffer size. Why? Because why I haven't used modulus symbol in the sense it is a circular queue. So after the last but one element has been completed, again you need to come back to first one. So you please try to observe that after placing one item, the counter value is incremented. The counter value is incremented. In a similar manner, if the consumer want to consume any item from the buffer, first of all you need to see that whether there is any items in the buffer or not. If the counter value is equal to 0, that implies there is no items on the buffer. You are not allowed to consume any item from the buffer. So you need to wait until, that is, do nothing. In case if counter is not equal to 0, immediately you are entered in this line. You are taking one element using out pointer, then out is equal out plus 1 buffer size. And after removing one item from the buffer, counter value is decremented. Now we observe it. Producer is incrementing count value. Consumer is decrement value. This producer process, consumer process, both are sharing a common variable. Call it as counter. Producer is incrementing, consumer is decrementing. Now, how we enter into inconsistent state, we'll see. Let us take. Suppose, let us take an example. If how counter is equal to count plus 1, counter plus plus. Already everyone knows that. You are all familiar with compiler design. What is a compiler? A compiler is a program which takes your high-level language program as an input and converts into machine language. But internally, high-level language program is not directly converted into machine language. First of all, high-level language program is converted into assembly language. Assembly language after the consumer is retrieved one item. Now, what is the count value? Again, it becomes 5 only. Why? Because initially producer producing an item into the buffer, it becomes 6. And after the consumer retrieved one item, again it back to 5. But what happens is that if you are not providing any security mechanism for this count, your answer is either counter value is copied in register 2. What is the counter value? Still it is 5 only. Why? Because the updated value is on only register 1. This value is not copied back onto register. Now, this consumer is reading a value from the counter. The value is again 5. 5 minus 1, it becomes 4. Now, time T4, register 1 value is updated to counter. Now, what happens? The 6 is overwritten. After that, overwritten by consumer with 4. The answer is 4. Suppose in time T4, if consumer is done, time T5, producer is done. In that case, initially 6 is updated and after that 4 is updated. Otherwise, initially 4 is updated, after that 6 is. In either of the cases, either T4 or T5 or this producer execute counter is equal to register 1 at T4, consumer execute counter is equal to register 2 at T5, or otherwise in time T4 consumer execute counter is equal to register 2 and producer execute counter is equal to register 1 at time T5. In either of the cases your answer is either 4 or 6. Either of the case your answer is either 4 or 6, but original answer is 5. This is called it as data inconsistency. This is going to be called as data inconsistency. So in order to overcome this inconsistent state, now we're using process synchronization. So what is inconsistent state? In case if any data, that is counter is a variable which is shared by producer and consumer, if you are not using any proper security mechanism for this particular variable, hence the data is in inconsistency. So whatever the techniques you are going to be uses for protecting these particular variables, always provides a consistent value, is going to be called as process synchronization. So now, one scientist has been told, how can you say that our data is inconsistent? Whatever the algorithms we have been written, whether these algorithms produces consistent value or inconsistent value, how do you tell it? Then they have been told one technique, call it as critical section problem. They have been told critical section problem. What is this particular critical section? So it is a good definition. We'll see a little bit. Okay. Now already we have been told, we have been predicted one definition. We already told one definition. It's called it as, what is a process? A process can be thought of as it is a program in execution. The process can be thought of as it is a program in execution. This is one definition what we have been seen for process. Another definition we have been seen for process is that a process is a continuous collection of CPU and IO burst cycles. A process is a continuous collection of CPU and IO burst cycles. Now we'll see another definition of process. A process is a continuous collection of critical and remainder section. So first of all, they have been defined. What is a process? A process is a continuous collection of critical and remainder sections. What is critical section? What is remainder section? What is critical section? What is remainder section? A process is divided into critical, remainder, so on to like this. Critical in the sense, a critical section is an area of a process. While executing such kind of an instruction, it is affecting common variables. It is affecting common variables that implies shared by other processes. Then such kind of an instructions are going to be called as critical section. Critical section is an area of a process where while executing such kind of an instruction, it can affect the common variables. And number two, remainder section. What is remainder section? While executing such kind of an instructions in a process, it does not affect any other common resources. That's it. This is what is going on. Okay, now each process has a critical section segment of code. Process may be till common variables, updating a table, okay, writing it to a file. That is, the common data is updated. And please try to see that it is very, very important. In case if any process is executing in its critical section, then no other process is allowed to execute in their critical sections. That is, the maximum number of processes that can be allowed to execute in their critical sections is only one process. Okay, now you please observe it. So, what is a critical section? Critical section is a set of instructions in a process. While executing such, it can affect the common resources. That is, variables or updating a table or writing a file, something. Whereas in the case of remainder section, while executing such kind of an instruction, it does not affect any common resources. Okay, and very, very important thing is that in critical section, in case if any process is executing in its critical section, then no other process allowed to execute in their critical sections. That is, the maximum number of processes that can be allowed to execute in their critical sections is only one process at a time. Now, let us see with a small example. Now, consider there is n processes are running in my computer system, P0, P1, so on up to Pn minus 1. These are all sharing some variables. Okay, they're all this one. Okay, in case if any process is executing, suppose let us take if P1 is executing in its critical section, then no other processes are allowed to execute in their critical sections. The maximum number of processes allowed to execute in the critical sections is only one process at a time. But what happens is that before entering into a critical section, first of all, you need to take a permission from the operating system. Your operating system will verify whether any other process is already in critical section. They'll simply ask you to wait. If no other process in critical section, then operating system will allow you to enter into critical section. Thus, kind of a checking is going to be done in entry section. That is, this is entry section. That implies in case if any variables you require, lock on that. Already I told that the best mechanism for protecting data sharing problem is locking. So before entering into critical section, first of all, you have to make a locks on the data items. That locking is done in entry section. And one entry section is done, the locks are properly obtained, you are allowed to continue, execute, it is critical section. Once critical section is completed, again, you need to release the locks. The releasing of locks is going to be done in exit section. It is going to be done on exit section. And the last one is reminder section. It can be executed any moment of time. Why? Because while executing such kind of an instruction, it does not affect any other processes. That's why reminder section can be executed at any moment of time. There is no problem. And that's it. Now, sir, how can we check? Suppose you have written an algorithm. That is, we'll define a process. Then after that, we'll see the algorithms. The process can be defined as, now, the third kind of definition. It is a continuous collection of critical and reminder section. Now we'll see how I will define a process. Do, until, while true. This is do. Entry section, first of all, obtain a locks and the common data items. Then you are allowed to continue the critical section. Once your execution is complete, you need to return back all the resources. That is releasing of locks is going to be called as exit section. And this is reminder section. Entry section, simply allocating of resources. And that is whatever the locks you are going to be required to execute. Whatever the locks you are going to be required to affect your common resources, it is going to be obtained in entry section. Once your execution is successfully completed, you need to release the locks. That is done in exit section. And this is reminder section. This is continuous critical reminder like this. Now, whatever the algorithms we are writing, for seeing the data is always inconsistent, you need to check these three conditions. If these three conditions are satisfied, 100% pakka that the data is always in consistent state. Okay, it is guaranteed serializability. This is the topic how we are going to learn in DBMS with the concept of serializability. The interleaved fashion of execution of schedules must be always in consistent state is going to be called as serializable. Schedule is said to be serializable. The interleaved fashion of execution, giving always consistent answer, is going to be called as serializable schedule. Now, what is this three condition? This is called as critical section condition. A solution to the critical section problem, whatever the solutions you are written, that solution must satisfy the following three requirements. So coming to the first requirement is that mutual exclusion. What is mutual exclusion? In case if any process is executing in its critical section, then no other process is allowed to execute in their critical section. The maximum number of processes that can be allowed to execute in their critical sections is only one process at a time. What is mutual exclusion? If any process is executing in its critical section, then no other process is allowed to execute in the critical section. The maximum number of processes that can be allowed to execute in their critical sections is only one process at a time. That is, if a process PI is executing in its critical section, then no other process can be executing in the critical section. The maximum number of processes that can be allowed to execute in their critical sections is only one process. Coming to the second one, progress requirement. What is progress requirement? Whenever the CPU becomes idle, you need to select one job from the ready queue and supplying the CPU and make the CPU busy at all the times. That is, while selecting a job from ready queue, you need to give a first priority for the process those who are trying to enter into critical section. Why? Because reminder section can be executed any moment of time. While executing reminder section, no other process are going to be affected. That's why we are always trying to give a first priority for the processes those who are trying to enter into critical section. That is progress requirement. That is, whenever a CPU becomes idle, you need to select one job from the ready queue and supplying the CPU and make the CPU busy at all the time. While selecting a job from ready queue, we need to give a first priority for the processes those who are trying to enter into critical section. That is, again, if no process is executing in its critical section, there exists some process that will be entered into the critical section. Then only those processes are that not existing there, reminder section can participate in the decision of which will enter its critical section next. So critical sections cannot be postponed. We must always giving a first priority for the process those who are trying to enter into critical section. Number 3, bounded waiting. What is bounded waiting? There exists a practical limit that each and every process is going to be allowed into the critical section. there exists a bounded waiting time each and every process allowed to enter into the critical section. What is the meaning of this? So once a request is made by a process, immediately it cannot going to enter into critical section even though if it is high priority. Why? Because the minimum time that is required to switch from one particular process to another process, just now we haven't seen in the last previous session, we need to determine who is having high priority, and we need to do context switch, and after that inter-service routines has to be executed. This is the minimum amount of time that is required to switch from one particular process to another process. That implies there exists a bounded waiting time for each and every process to allow into critical section. If once an interrupt has been given, immediately you are not allowed to enter into the critical section. That is bounded waiting. That is bounded waiting. In a similar manner, okay, suppose if a high priority process, every time high priority process is not only allowed to enter into critical section, we need to give some priority for the other processes also. That's why we are using aging concept. Okay, that is also going to be considered. These are three requirements that must be satisfied for any critical section problem. Mutual exclusion, the maximum number of processes that can be allowed to execute in the critical sections is only one process at a time. So whenever a CPU becomes idle, we need to select a job from the ready queue, those who are having enter into critical section. So we need to give a first priority for the processes, those who are trying to enter into critical section. Number 3, there exists a bounded amount of waiting time that can be allowed to each and every process enter into the critical section. And the second one, there exists a practical limit on each and every process that can be allowed to enter into the critical section. So how do you understand this one? So we'll solve this one by using some problems. Okay, these problems are already we got in so many GATE examinations. So I haven't taken sample questions from that. I haven't written on algorithms and see that which conditions are satisfied in that algorithms and which conditions are not satisfied. Now we'll see. This is two process solutions. There is various questions which is coming on GATE. We'll see. Okay, there are two processors running, process PI and process PJ. There are two processors running. These two processors sharing some common variable X. Let us assume PI and PJ. There are two processors running in my computer system. These two processors sharing a common variable X. These two processors sharing a common variable X. These two processors sharing a common variable X. Now, let us take how do you, okay, so while executing process PI, you please try to see that, okay, process PJ is not allowed to modify X while executing process PI on X, that is while modifying the value of X by PI. At the same time, process PJ is not allowed to access or modify X. In a similar manner, while executing process PJ on X, that is while modifying the value of X by PJ, at the same time process PI is not allowed. That implies if process PI is in critical section, then process PJ is not allowed to enter into the critical section. Similarly, if process PJ in its critical section, then process PI is not allowed to enter into the critical section. Now, how do you solve this particular problem? Okay, it can be solved by using a single variable called as turn. Suppose if turn is equal to I, then process PI is allowed to enter into the critical section. If turn is equal to Pj, then means process Pj is allowed to enter into critical section. That implies if turn is a variable that contains only one value, that is either I or j, that implies only one process can be allowed into critical section. So that clearly you can understand is solving the problem of mutual exclusion. Why? Because the maximum number of processes that can be allowed to enter into the critical section is only one process. If PI is in critical section, the term is equal to I. So that PJ is not allowed to enter into the critical section. If PJ is equal to, if term is equal to J, then where process PJ is already in critical section, then process PI is not allowed into critical section. So a simple solution is that if term is equal to I, process PI is allowed to critical section. If term is equal to J, process PJ is allowed to critical section. Now, however, process PI algorithm have been written like this. So first of all, while if term is not equal to I, turn is not equal to I. That means what? That is turn is J. That implies at that time the process Pj is already in critical section. If turn is not equal to I, sorry, you are not allowed to do any operation. No. So you are going to be stuck in this while loop. So simply you are waiting for your turn value becomes I. Until then you have to wait. And after that, in case if turn is equal to I, immediately you are allowed to enter into the critical section. And after that, once your successful execution is complete, you need to release the resource. That is again immediately you are making turn J, and you are giving an indication to process Pj. Come on, you are allowed to continue. The remainder section can be continued at any moment of time. That is, now this is going to be called it as entry section, and this is exit section. You may call it as this is locking section, and this is unlocking section. Now, similarly for process Pj, if process Pj want to enter into the critical section, if process Pj want to enter into the critical section, first of all, it checks that whether turn is equal to J or not. If it is not J, then immediately you are simply no operation. That implies you are not allowed to enter into the critical section. That implies at the moment already process Pi is executing in critical section. After completion of that, you are giving the turn is equal to I. Then you are giving an indication to Pi. Come on, you are allowed to enter into the critical section. And remainder section can be executed at any moment of time. That's see that. Okay, if process Pi in its critical section, then process Pj is not allowed. Process Pj in its critical section, then process Pi is not allowed. In this algorithm, the mutual exclusion is 100% satisfied. Number 2, progress requirement and bounded waiting is not properly specified. That implies, what is the meaning of this? What is a progress requirement? Whenever the CPU becomes idle, we need to give a first priority for the processes, those who are trying to enter into critical section. So such kind of a measures is not clearly mentioned here. And bounded waiting, there exists a practical limit on each and every process can be allowed to enter into the critical section. There is no such kind of a thing is discussed. That implies in exam, the algorithm satisfies only mutual exclusion, progress requirement, bounded waitings are not satisfied. Now, another guy has came and given another solution for two process. Same process Pi and process Pj. There are two processes running in a computer system. Process Pi and process Pj. Okay, there are two processors running in a computer system. Both are sharing common variable x. So in order to protect the variable x, I have been taken flag variable. Okay, now the flag is defined as it is an array of 0 to 1 of boolean. It is having either true or false values. Now, if process Pi want to enter into the critical section, then flag I must be true. If process Pj want to enter into the critical section, then flag J must be true. So before, if a process Pi want to enter into critical section, first of all, he has to make his flag true. And after that, immediately you need to check that whether process Pj is already in its critical section. And in case if it is done, you need to wait until the flag J becomes false. Similarly, if process Pj want to enter into the critical section, first of all, you need to set this flag true. And after that, it checks that if flag A is already set to true. If it is already set, that implies process Pi is already before you, so that you need to give a first priority for process Pi. That's it. Let us say how the solution has been written. Repeat, if a process Pi want to enter into the critical section, initially the flag I becomes true. Then immediately process Pi checking that whether flag J is already set before me. That is, I am given first priority for the process, those who are already trying to enter into the critical section. That is, if flag J is already true before me, so that I am not eligible for executing critical section, that's why no operation. If flag J is not true, then I am allowed to critical section. Once my task is complete, again I will become my flag is false. Now I am not in competition. I am not in competition. The CPU will going to be given a first priority for those flags are is equal to true. The CPU will going to be giving a first priority for the process. Those flags are true. Okay. This is how we are going to be similarly implemented for multi-process also. And another section can be executed at any moment of time. Now let us see. If flag J is equal to if Pj wants to enter into critical section, if Pj wants to enter into critical section, first of all, process flag J must be true. And before entering into critical section, it checks that if flag A is already setted before. In case it is setted before, we need to give a first priority for the process PA. This is entry section. And in case if flag A is not true, then you are going to be critical section. And after that, flag J becomes true, false. That is your coming exit section. And the run section is executed. Now you clearly observe it. Okay, clearly observe it. Mutual exclusion is partially satisfied. Mutual exclusion is partially satisfied. Why I am telling this partially word, I'll tell you. Let us take an example. First of all, I'll tell you how mutual exclusion is satisfied, then I'll derive the word partially. So, flag A is equal to true. Then I'm checking that if flag J is already true or not. In case if it is already true, I'm checking it. That implies if process Pj is already in its critical section, then process Pj is not allowed to continue. In a similar manner, here also, process Pj sets its flag to true. If process flag process PA flag is already true, process Pj is not allowed. That implies the maximum number of processes that can be allowed to execute in the critical section is only one process at a time. So that mutual exclusion is satisfied. So that mutual exclusion is satisfied. Except in one situation. Except in one situation. What is it? So, in case if you implement an algorithm like this, it may be structured in infinite loop. How? So let's take an example. There are two process PA, both are running concurrently. In time T0, flag A is true. In time T1, flag J becomes true. Then what happens? In time T0, flag A is true. Time T1, flag J is true. Now in time T2, it checks for whether flag J is true or not. Yes, flag J is true. So that it is structured in this loop. And T3, then it goes here. Flag A is true or not. If flag A is true, then it is also not allowed to. Now, both processes are continuously structured in this values. No process is executing. So, it is infinite loop. It is an infinite loop. So, process Pi makes its flag true and waiting for flag J becomes false. Process Pj makes its flag true and waiting for flag A becomes false. So, both are not allowed to continue the execution. And so, this kind of a situation is in indefinite blocking. This is indefinite blocking. That immediately enter into critical section. And seeing that if any other one is setted flag before me, that implies I am giving a first priority for the processes, those who are already trying to enter into critical section. Understood? I'm process PA making this flag true and checks that flag, the process PJ is already setted flag true or not before me. In case before me, that implies that process is allowed first and I am second. I am giving first priority for the processes, those who are trying to enter into critical section. Okay, that is, I clearly told that progress requirement is satisfied. But there is no clear specification that, okay, bounded waiting. There is just a practical limit on each and every process allowed into critical section. There is a, okay, how many number of times each and every process is allowed into critical section? No. That's it. So in exam, only progress requirement is 100% satisfied, mutual exclusion is partially satisfied. This is an answer for this algorithm. And the complete solution for this is, now another scientist came and merged the above two algorithm and written a 100% solution. This, all three conditions are satisfied in this. What is this? We'll see.
Hi, bye.
And now, so in this algorithm 3, process PI and process PJ both are executing and both are sharing a common variable. Both are sharing a common variable x. Now, in order to protect this variable x, I am taking two variables, turn and as well as flag. Turn is equal to, it may be I or j, and flag is equal to flag I is true and flag j is false, and flag j is true or flag I false. Now, what is the conditions for entering into critical section? If process pi want to enter into critical section, turn should be I and flag I should be true. Similarly, if flag process pj want to enter into critical section, flag j must be true and turn is equal to j. That's it. In both the cases, flag values may be true, but turn may be either I or j. Only one value can be allowed in a variable, so that only one process can be allowed into critical section. There is no concept of infinite loop in this from theory. So, if a process pi want to enter into critical section, the flag I must be true and turn should be I. If process pj want to enter into critical section, flag j must be true, turn must be j. That's it. And now we'll see how to write a code for this. How to write a code for this. How to write a code for this. Process pi, I'm writing. If the process pi want to enter into critical section, process pi want to enter into critical section. Initially, he has to make his flag is equal to true. And he's not making turn is equal to I. He's making turn is equal to j. Why? Because I am giving a first priority for the processes. Those who are already set the flag true, even though if switching is happened, even though if time slice is complete, control is come to me, I am giving first priority for j, process bj. That implies, it clearly states that, okay, I am giving first priority for the processes, those who are trying to enter into critical section. Now we'll see in entry section, if flag j is true and turn is j, that implies already process pj is in its critical section, then you are not allowed to continue the execution. You are simply stuck in this loop. Suppose if it is not done, then you are allowed to continue the critical section. Once critical section is done, you have to make your flag is false, which is called as an exit section. This is called as flagging. Then remainder section can be executed at any moment of time. That's it. In case 2, process pj. Process pj. So if the process pj want to enter into the critical section, initially makes its flag is equal to true. Initially makes its flag is equal to or true, and after that it makes turn is equal to I. Okay, immediately process pj is not allowed to enter into the critical section. It's giving the first priority for this one. That is, while flag is equal to I, flag is true and turn is equal to I, that implies the process PA is already executing in its critical section. So I need to wait until the process PA has to be complete. And after that critical section, then after that making my flag is equal to false. Remainder section will execute. Now, from clearly, while executing process PI, process PJ is not allowed to continue the execution. While executing process PI is not allowed to continue the execution. So in this situation, either process PI or process PJ, okay, only one is going to be allowed. In case if the both are going to be setting the flags at successive clock pulse period time, but the turn value is either I or J, okay, so only one process can be allowed into the critical section. There is no concept of blocking. So mutual exclusion is present. So mutual exclusion is satisfied. So in order to check whether condition 2, that is progress requirement and bounded waiting, Okay, so for second one, progress requirement. So progress requirement in the sense, I am always giving a first priority for the processes. Okay, those who are trying to enter into the critical section, process PI making turn is equal to J. That implies process giving a PI is giving a first priority for the processes, those who are already trying to enter into critical section. Similarly, process PJ is also making its turn is I. That implies so process PJ is giving a first priority for the process of PI who's are already trying to enter into the critical section. So condition 2 is satisfied and bounded by time. We note that process PI can be prevented from the entering into the critical section only if it is stuck in the while loop with the condition flag j is equal to true and turn is equal to j and turn is equal to j. Then loop is only one. If pj is not already in its critical section, then flag j is becomes false. If we are not in critical section, flag j becomes false and pa can enter into the critical section. If pj has been set flag j is equal to true, also executing in its while statement, then either a turn is equal to I or turn is equal to j. That is, it is satisfies second one. However, once pj is exists in critical section, it will reset the flag j is equal to false, allowing pa to enter into the critical section. If pj resets flag j true, it must also set the turn is equal to I. Turn is equal to I. This is equal to turn is equal to I. Thus, since pi does not change the value of variables turn, okay, while executing while the statement pi, when pi will enter the critical section. Properties after almost entry by pj, that is, there is no concept of bounded waiting. That implies this kind of solution is satisfies all three: mutual exclusion, progress requirement, and boundary waiting. Suppose this is have been written an algorithm for only two processes. You can also implement this algorithm for multi-processes, that is called as multiple process solution, which is also known as Bakri algorithm. So in that, what you need to do is that in case if any process want to enter into the critical section, first of all, he has to check that he has to set his flags equal true. Then he has to set his priority. Currently, whatever the number of processes are running, that that process priority plus 1, so that it is the next high priority. So whenever the CPU becomes idle, so you need to select one job from ready queue who is having high priority. The high priority has to be serviced first. Suppose in case if any process in its critical section, then you need to check that no other n-1 process are allowed to enter into the critical section. Once your critical section is completed, your priority may be set to 0. Why? Because you are not allowed to, you are not in the computation. So the competition is only between, the competition is only between the processes who are trying to enter into the critical section. The processes who are trying to enter into the critical section. That's it. Okay, that is. This is how do you write a software solutions for protecting a data which is shared by more than one process, which is not allowed into critical inconsistency. Now, this can be also be implemented. Solution can also be implemented by using hardware. That's why it is going to be called as, the title is given as synchronous hardware. The title is given as synchronous hardware. The title is given as synchronous hardware. What is this? Before going to the detailed discussion about, in this we are going to see some of us technique. Now we're going to see some of the techniques. What is synchronization hardware? So many systems, many computer systems provide hardware support for implementing critical section code. Many computer systems provide a hardware support for implementing critical section code. You know what is a critical section? Critical section code is nothing but while executing such kind of a code, no other process is allowed to enter into the critical section. Critical section is a set of instructions. While executing such kind of an instructions, it can affect the other resources. So that you need to see that the maximum number of processes that can be allowed to enter into the critical sections is only one process at a time. Okay, that's enough. The solutions, whatever the solutions you are going to be chosen, Okay, whatever the solutions you are going to be choosing from the books or from the literature or from the research papers, all solutions are based on the idea of locking. So what is locking? So before executing any particular process, first of all, what are the resources which is going to be required? First of all, make a lock on that resources. One lock is done, we are allowed to continue in the critical section. Once your lock is process is execution is complete, you need to release the lock. So making the lock is called it as entry section. Executing a process is called it as critical section. Releasing a lock is called it as exit section. That is protecting critical regions via locks. So already we know that we are having two kinds of things. Number one, we have uniprocessor solutions and multiprocessor solutions. So either uniprocessor or multiprocessor solutions, whatever it may be. So let us take first one, uniprocessor. Uniprocessor in the sense there exists only one processor reside in your computer system. Uniprocessor in the sense there is only one processor reside on a computer system. There is one processor in the sense. In case while executing one process in its critical section, simply what CPU does is that disabling the interrupts. Already I told that maskable, non-maskable classification of interrupts. Maskable, that can be ignored by the processor, it does not cause any problem to the CPU. Suppose while executing one process in critical section, simply you can mask or disable the interrupt. So whatever the interrupt which has been generated from any processes, I cannot handle, then the data is 100% guarantees consistent state. That is the currently running code would be executed without any preemption. That is, whatever the critical section code now you are executing, it cannot be preempted, it cannot be forcibly stopped and giving the control of the CPU to another one. But which is generally too inefficient on multiprocessor systems. So multiprocessor in the sense more than one CPU can be simultaneously reside on a same machine. They are closely communicate. So while execute one binding for a lock of one particular process, remaining all the processor has to be wait. That's why it is very inefficient. Already we told you one example, Tatkal service. If one person is making a reservation by making a lock on railway reservation number of Tatkal, what remaining all the people are not allowed. No, you should allow them. All the people can concurrently use it. But only thing is that if any modification is done on one particular processor, the modification has to be reflected to remaining all the processors at the same time. This concept already we have been known it as coherency and consistency. What is this coherency and consistency? What is this coherency and consistency? Coherency and consistency in the sense, and that implies if any processor makes an updation on the local cache, you please try to see that the updation should be done in all the local caches of the CPU at the same time. Otherwise, the data is an inconsistency. Okay, that is. And the operating systems using is this, not broadly scalable. That is. Now, today, the modern operating systems, the modern machines provide a special atomic hardware instructions for protecting a common variables which is shared by more than one processor at the same time. So now today the modern machines providing a special atomic hardware instructions, for securing a data which is shared by more than one process at the same time. Okay, that is atomic. What do you mean by atomic? Non-interruptible. Please remember this. Atomic, non-interruptible. At a time, it can be accessible by only one person at a time. At a time, it can be accessible by one person at a time. You please remember it. Atomic, the word stands for non-interruptible. That is, at a time, only one person can be eligible for accessing such kind of resource. So, these particular variables can be setted. Atomic variables can be setted. Okay, before that, if you want to set atomic variables, you need to test and then set. That's why test memory word and set a value. We'll see what is that mean by. Okay, so now again I am defining process. Okay, again I'm defining a process. Already we have been seen. Okay, already we have been seen in the last class. In the previous one, a process is a continuous collection of critical section, remark section, so on up to like this. Okay, every critical section is having entry section, exit section like this. Now again I'm redefining the process as, first of all, acquire a lock on the data. First of all, acquire a lock. Whatever the data you are trying to access, first of all, acquire a lock on it. Once a lock is obtained, operating system is given a permission to you, then you are allowed to enter into critical section. And once you have been completed, you have to release your lock. It is exit section. This is exit section. Sorry, some small arrow is different. This is called it as exit section. Releasing a lock is called it as exit section. And coming to the next one, remand section can be executed any moment after. This is a simple process definition. Now, how do you test and set the lock? Okay, how do you test and set the lock? That value is either true or false. That value is true or false. Now, I'm defining a Boolean test and set function like this. It is taking like this a target, and target is equal to return the value as an answer. Now, do so in case if any process want to enter into the critical section, first of all, it execute a function test and set. If the lock is given as true, okay, that implies if some guy is already executed against critical section, you are not allowed to enter into the critical section. If it is true, then you do nothing. If it is written as false, then you are allowed to enter into the critical section. Once your critical section is complete, again you have to make your lock is false. That is, you are not in competition. That is, you are not in competition. That is not your competition. So this process is going to be repeated until the whole execution is complete. So clearly the solution says that only one process can be allowed to enter into the critical section. If the lock is true, someone is already running. So you have to wait until the lock value becomes false. In case if lock value is okay false, that CPU is now that variable is not. Simply you can also done by means of like this 0 or 1. 0 in the sense it is not used by anyone. This kind of a discussion we'll see at a later stage like a binary semaphore. Okay, 0 is unlocked, 1 is locked. So in case if any processes want to access that particular variable x, first of all, it try to see the value is 0 or 1. If it is 0, that implies it is not locked. Immediately you can access it and make the lock value is 1. And after that, if any guy want to access that one, it first checks that what is the lock value. If the lock value is 1, that implies it is true, you are not allowed. Then you have to wait until the value becomes 0, it becomes false. There. So simply by using this small function, I can protect my variable. Is it clear? This is a hardware kind of a solution. Now we'll move on to the software kind of a solution is going to be called it as semaphores. Okay, and this will going to be discussed you on next class. Okay, time is not sufficient. Allow me to continue further. So this is what we have been seeing at a glance. What we have been seeing today is that process synchronization. Process synchronization is a tool which can be allow you multiple process can be allowed to concurrently execute it and sees that the data will not going to enter into inconsistent set. This is completes our discussion about today, and the rest of the discussion we're going to see you on tomorrow. Thank you. Can I stop the session? Is anybody there? Is anybody there? Can I quit the presentation now? Yeah, okay. Now I'm leaving. Yeah, fine. Everything is fine there? Yeah, fine. Thank you.